Boom. Okay, so anything here? So we're going to get started then on Amazon. Okay, our coverage. First of all, transaction scale, process and principles, and eventually we'll get into two-phase commit transaction model. That's kind of the core of this lecture. Then a little bit afterward, we'll talk a little bit about network architectures, client server, and N-tier architecture in a little bit of detail, and then object description languages. So that's what we're going to do today. Not all of that today. So Amazon is big. In case you didn't know, Amazon is really, really, really big. Lately, with the whole COVID quarantine, they've been getting $280 billion in annual sales. Actually, I believe that's 2019, so even pre-COVID. I'm not sure where the cutoff was. So yeah, they're huge. Right now, they're actually over 50% of U.S. e-commerce. So you take all the other online retailers and operations put together, they're not as big as Amazon. That's crazy. On top of that, they're not just a huge retailer, they're also the world's largest public cloud service. If you've ever heard of Amazon Web Services or S3, their simple storage system, yeah, they're huge. Now, because they're so big, they obviously are going to get a tremendous amount of network traffic. So Amazon all by itself has to process hundreds of transactions per second. Every transaction, right, every time somebody shows up and buys something, of course, there's going to be a whole lot of related browsing, right? People are going to go to the Amazon site, they're going to look at web pages, they're going to browse around for a while, and for every 10 or 20 or 40 web pages they see, maybe they're finally going to buy something once. Okay, so there's a lot of traffic Amazon has to maintain by itself. But Amazon's cloud network, the entire cloud network by itself, can actually handle over 1 million transactions per second. It is a very impressive, gigantic system. Okay. So, little breakdown of revenues. AWS, Amazon Web Services, is almost 10% of everything. About 2/3 of it is retailing. About another big chunk, 17, right? About half of what's not Amazon's retail is third-party sellers, people selling through Amazon. Other stuff, Amazon Prime, other retail subscriptions, and various other co-branded credit card agreements, for example. But, 84% of their operation is retailing. A big chunk of the rest is their cloud service. Okay. Now, when we talk about Amazon's transaction volume, thing to keep in mind, these transaction rates, they're averaged over the entire day. So roughly speaking, they're going to be about double during regular shopping hours, right? Most of Amazon's operation is from North America. And so, yeah, it's going to be when North America is daylight hours or early evening, that's when a lot of the Amazon traffic is going to happen. And of course, multiplied during major shopping events. Amazon Prime Day, for example, was lately so big that even Amazon itself had trouble keeping up with all of that network traffic. And it's still growing, right? Saw a chart the other day. Amazon has been growing in the middle double digits for the last 5 years now, so something like 40% a year. Now, every time there's a transaction, of course, again, there's a lot of extra information that has to get transferred around. So the actual transaction details, what items are getting bought, the credit card number, your address, all that sort of thing. There's also supporting information, everything that's shown on that web page, right? All the text, the pictures, the video, browsing around the purchase, and a whole bunch of secondary transactions. Okay, so let's talk about secondary transactions for a moment. Okay, so suppose down here, we're going to draw some boxes. This is Amazon. I don't like that font for Amazon. Let's do, should we just do Arial? Where is that? Boom. Yeah, that looks Amazon-ier. Okay, and let's suppose up here in the corner, this is me. I buy something. Okay, so I go to Amazon, I buy something. All right. And then what happens next? Well, there's a whole bunch of related things that are going on. I'll do these as secondary transactions, even though they're not, especially specific. That can be that. Let's do green. Okay. So what else does Amazon have to worry about? Well, when you buy something from Amazon, you're not paying in cash, right? You're paying with a credit card. So there has to be some sort of interaction with a credit card company. What else? Well, Amazon maintains all kinds of internal analytics, right? So I'm going to mark that down as web analytics, just generally analytics. Everything that people did, right? So actions on pages, who bought what, various recommender updates, updates to the recommender system, okay? All that stuff. And then last, shipping, right? Shipping services. So, right, supply chain management generally, shipping and SCM. Okay. So all that sort of thing, all that Amazon has to interact with all these other services, right? So there's a whole lot of stuff going on. It's not just you show up, you get a web page, boom, there's a quick transaction and you're done. There's a whole lot of network traffic that Amazon has to manage. Okay. So to be competitive, right? Amazon, other large retailers, this is all what they're doing now. They have to either deploy their own high capacity cloud services or rent the service from others. Amazon's big enough it can use its own. The other big retailers, you know, like the Target and the Walmarts of the world, they're still big retailers, but, you know, they're not as big as Amazon. Okay. So, transactions. What do we mean by transactions? Well, when we talk about transactions among ordinary humans, we just mean exchanges that involve some kind of payment. So typically some kind of reciprocal release of goods. For example, I buy something, so I give you some money or I give you my credit card info. You make the, I owe you some money that I'll pay off eventually, and you send me the goods. Or it could be clearing an existing obligation, right? So you have this credit card bill, you go into the bank site to pay it. However, the database view is similar but different, right? It encompasses this consumer view, but there's more to it. So database view, any action that's a single logical unit, for example, buying something, right? But it could encompass multiple operations. For example, you go to create your own new customer account, right? At the very least, Amazon is going to need a whole bunch of information from you. You may go through multiple screens. For example, you may have one to enter your information. You may have another thing to set up your password. You may have another if you want to immediately apply for a credit card. All those things together will get bundled into potentially one transaction. Updating database contents. For example, you buy something on Amazon. It has to make updates in a lot of different systems. For example, the list of things that you've bought in your own customer history, the ranking of that item, right? How many people have bought it in the last year or so. It's going to show how it lines up in the list. There's going to be echoes to suppliers, perhaps. If you buy the last one or it's starting to run low, Amazon may have to send a notification to a supplier to get more stuff, right? So all of these kind of things, they can all get bundled together into a transaction. Even processing a query, right? You say to Amazon, I'm going to enter some text into the search box and show me all the products that match this. Amazon sends you the results. That's a kind of transaction. Okay, so an action that's a single logical unit, but could encompass a whole set of operations. Okay. So that's what we mean when we talk about transactions. Now, most of the time, it'll be clear that we're talking about transactions in a generic sense, but when we get to the two-phase commit model for transactions, it will be clear that we're talking about database transactions. Now, brief history of Amazon. 1994, so flashback to then, the internet was basically a specialized tool for government, military, research, education, that sort of thing. So if you were in one of those areas, yeah, you probably had access to the internet, but it wasn't something that most people had in their house. There were only a few million internet users at the time. In 1994, Amazon started seller. What they were trying to do is circumvent a lot of the major inventory challenges of physical stores. Well, that was freaky. I don't know whose feedback I got there. Okay, so we'll give a little detail for that. So when Jeff Bezos was thinking about what he was going to do, as far as, what kind of business he was going to start, what would be suitable for an internet business. He looked at a bunch of different options, but the one he eventually settled on was books. And we can ask why. Well, number one, they're what's called a commodity good. Nobody really cares who they buy the book from because it would be the same book. Okay? So it's a commodity good. So there's no differentiation there. Okay? Number two, booksellers have a lot of practical troubles. Okay? Physical bookstores. I'll say this, physical or brick and mortar, B&M, but physical booksellers, physical stores, booksellers. Okay? What are some problems? Well, number one, I don't know what happened there. Oh, okay, lock that. Okay. Sorry, something's weird here. Okay, things jammed up for a second. Okay, number one, retail theft, internal and customer. So people go into bookstores and they steal shit. Okay. In practice, that's not really going to be a problem for an online seller. First of all, because initially the system was small enough that he could basically manage it himself. He wasn't going to steal from himself. But number two, even when it gets bigger, you can monitor employees much more closely than you can customers without getting any kind of negative feedback, right? You just watch people and say, oh, you're leaving the warehouse with a bunch of books under your coat. No, you're not going to do that shit. Okay, so that was a big one, retail theft. Number two, limited inventory. Okay, can only carry what fits in the store. On top of that, what else? Depreciation and related costs, right? Lots of books sit on the shelves for a long time, maybe years. Okay, that's money that you're losing because you bought the book and it's just sitting in your store doing nothing. All right, so now, of course, I'll add in one last thing. Even if a customer shows up and asks for a book and the store doesn't have it, sure, they can offer to order it, but usually the customer will say, no thanks, I'll check around. Okay, that's usually what happens because they went to the bookstore to buy it now. So if it's not there, the window's kind of closed. Okay, so advantages to Amazon. Okay, number one, infinite reach, right? Not limited to area around bookstores, right? There's a limit to how far people are willing to drive to a physical bookstore. Number two, what else? Deep product line, can offer any book from any publisher. Okay, that's a big deal. And number three, right, customers expect a few days wait. So that's not going to be an issue. That's built into the business model. Now, you could argue that depending on what's going on in the world, that maybe the physical bookstore, it's going to be able to get past those challenges, right? 1994, it was not clear what all was going to happen in the world. So 1994, not many internet users, but growing. Likewise, not much buying because of trust issues, right? People's like, oh man, I'm just going to give my credit card information to some random business that I've never heard of before. So those were two big issues that eventually played out in Amazon's favor. But yeah, there was a lot of what can you say? There was a lot of question early on whether Amazon would be able to sustain itself as a business model, right? Or whether one of these other companies, for example, one of the pre-existing large businesses that was a physical bookstore, would end up winning. But these were essentially the issues. Okay. So, as Amazon grew, though, it had to develop a lot of new systems to manage the scale problems, right? It starts getting bigger. As always, things that are simple on a small scale become very difficult to manage at a large scale. Simple stuff like website traffic, right? Websites in 1994 were not built to handle the kind of website traffic that you see now. So instead of just having one server that serves up web pages to people who come to visit, Amazon started needing a whole complicated architecture of a whole set of servers, and visitors to the site would connect to one of them. Transaction processing. Well, early on, the operation was basically run out of a dude's garage. As they got bigger, right, yeah, that was no longer feasible. So transaction processing, that had to be handled differently. Again, early on, when they're just getting, a few or even a few hundred orders per day, yeah, you can handle that by one guy running a copy of Excel and seeing what's there and calling up the publishers. As they get bigger, they have to develop automated processes for all this because you can't do all that stuff over the phone. Inventory management, right? Even though Amazon is just having the books arrive and packaging them and shipping them out, again, if you're doing a few hundred or a few thousand books a day, yeah, that's feasible to do in somebody's garage, just barely, but yeah, you can do it. But as they get bigger, they need a whole lot more space in order to process all those things, and they need more people so that they can do it quickly, and they need extra customer service on hand in case something goes wrong with the shipments, all that kind of stuff. Last, delivery. When Amazon is small, they're not going to have their own delivery service. They contract with UPS or USPS, whoever, FedEx, even if people are really desperate for speed. They contract with these operations and they'll get their stuff shipped, but they got to pay extra. But nowadays, you look around, you see the Amazon trucks, right? Amazon has its own fleet of trucks. They're working on drones for deliveries. We'll see how that goes. Anyway, they get bigger. New approaches become feasible and necessary. Okay. Now, early on, the first years or so of their existence, Amazon focused on retail operations. They were just trying to sell books, and they branched out a little bit into general retail. But when Amazon started selling digital things, they needed a whole extra layer of technology. So things like music downloads, or Amazon's Kindle for books, or Amazon Video, all that sort of stuff, digital things, streaming services, yeah, they need a lot more new tech in place. If you're just switching from selling books to selling DVDs, yeah, that's basically the same kind of operation. You can run it in the same way. But these digital products, they need an entirely new approach. So as Amazon got really big, eventually they had to design its own custom hardware and network systems, right? They got so big that they were growing so quickly, there wasn't anybody in the world that could operate as consultants for Amazon. They just said, well, we got to do it ourselves if we're going to keep up. So they developed practices and technology that were designed for their own needs, and the big one was scalability. When your business is doubling every year, that's what everything's going to be geared toward. You're going to be geared towards a system that's extremely flexible, and you can add on new capacity and still have everything be operational in the meantime. Now, there is a popular misconception that early on Amazon began renting out its excess capacity as cloud service. The idea is, well, they're busy with their retail half the day. The other half of the day, most of their systems are idle, not really doing anything. So Amazon thought, you know what? We can just rent out those machines, and that was the basis of cloud. Actually, that myth has kind of caught on because it has a certain intuitive sense to it for people that aren't really tech people. But the truth is, even though Amazon was mostly busy with routine network traffic during the day, during retail hours, at night, there's all sorts of other database stuff that has to go on. There are system updates that have to happen. There are various types of diagnostics and hardware maintenance that has to happen. So even though, yeah, in terms of network traffic, sure, they're busier during the day because of all that. But there's actually plenty going on all around the clock. And Amazon did not have a whole lot of excess capacity at any point in those early years. So the story about cloud is actually a little different. We'll talk about that when we get to the cloud lecture. Okay, so now, right, 2020, Amazon is a hybrid retail cloud services business. So most of the revenues come from retail. We saw in that little picture something like 84% from retail, but most of the network traffic comes from cloud services because that's basically what the cloud service is handling network capacity for other businesses. So we'll discuss Amazon's transaction processing system, but in the back of your mind, remember that it's only a fraction of their operation, right? Their entire cloud service is actually much, much longer. Much larger, rather. So Amazon maintains a competitive advantage by continuously innovating and building on its existing operations. It's designed that its operations, even though they get really big, they're not going to crumble and fail like, say, MySpace did. For example, dominating the book sector enabled expansion into other retail sectors. This is an example. Once you build the platform, if that platform is amenable to other product categories, you can expand it pretty painlessly. You don't have to develop an entirely new platform. You can keep most of your same existing setup, add a few extra machines onto it, and you don't pay much in the way of cost. Second, the technology required to manage scale actually formed the base of its cloud system. So the big thing that Amazon was dealing with early on is that it had a lot of third-party sellers. They wanted to sell their products through Amazon. Well, early on, Amazon was designing a whole bunch of custom interfaces for them to sell their products. At some point, some of the engineers in Amazon said, you know, this is nuts. We're spending all day trying to design these custom interfaces. Why don't we just make, you know, a limited set of interfaces, or ideally one, and then the retailers can just use those. They'll fit their web pages to that style. Yeah, well, that sort of standardizing the interfaces is the basis of cloud. So just like when you go to Facebook, doesn't matter who you are or where you're accessing Facebook from, it feels the same, right? If you're doing it on a desktop in New York versus a desktop in California versus, I don't know, a desktop in India, whatever, it's going to be the same. It's going to be the same feel to Facebook. Okay, same kind of thing with Amazon. All the operations, they're going through a standardized process. So in a sense, anybody who's showing up to use Amazon Web Services, it doesn't matter who they are or what they're doing, they're going to access their data in the same way. All right, so if you're interested, I have an article here about what's next for Amazon, although it is a little bit, doesn't exist, that's weird. It's a little bit out of date, so maybe it doesn't exist. Yeah, I think it doesn't. That's odd. Okay, well then, it used to exist, but now it no longer does. All right, so we divide Amazon's transaction process into the front end and the back end portions. So hopefully you've all ordered something from Amazon or some other similar online operation. So you know the basic process. Okay, customer logs into the Amazon site, browse around, add some items to the shopping cart. Eventually you check out, and then you select your delivery options, and finally you pay, right? That's all the stuff that the customer sees. That's the front end. The back end, right, that's the part that happens in the back, away from the customer's eyes. So behind Amazon's interface, you have a whole bunch of systems working together to process the order, right? So some of those are internal to Amazon, like Amazon's analytics, or if they're trying to schedule a shipment on one of Amazon's own trucks. Some of them are external, like connections with credit card companies or connections with other non-Amazon shipping services. And there's always going to be a cascade of database activity, right? So anytime you buy something from Amazon, they got to update their inventory, they got to update the ranking of that product, they got to update their analytics, whatever internal list they have about what products are hot at what day, they do that. There's messages going to the warehousing guy, say, hey, you got to pull this item, put it on a truck, get it to so-and-so by such and such a time. There's a lot of stuff going on when anybody buys a product. Okay, so that's the idea. So what we see, the front end, yeah, we see a little bit, but the real work, most of it's going on the back end. Okay, so simple standard process. You go to buy something, you put some things in your cart. Typically, they're going to be locked so that other customers, other site visitors can't buy them. So the grocery cart is analogous to a cart in a physical grocery store, right? Or your shopping cart. Whereas if you're walking around Target, an actual Target store, and you put something in your shopping cart, it would take a real asshole to just, you know, walk over to your cart, reach in, pull that thing out, put it in their own cart, right? People just don't do that. It would be unusual anyway. So same kind of thing happens at Amazon. Once you've put something in your cart, you have claimed the right to buy it for a while. Okay, so when you finally check out, your credit card gets validated and the payment gets processed, or right, maybe there's a fraud detection mechanism that says something like, well, this card is frozen, we don't think you're going to do it, or for some other reason the process gets aborted. If that checkout fails, then the items will be unlocked. Again, it's as if you go to Target, you're wandering around the store with some stuff in your cart, you go to check out, you give them a card, and the cashier says, I'm sorry, your card isn't working today. And so then you're like, oh, well, damn. And you leave the cart there with all the stuff, and eventually people come around and they take the things out of the cart and they put it back on the shelves. Okay. So once you've checked out, right, once you've formally decided that these are the items you're going to buy and you've paid for them, then the warehouse receives the order request, delivery arrangements gets made, inventory levels get updated, right? They say this thing is no longer in the warehouse, now it's on a truck heading to you, stuff like that. That's the sort of thing that happens. Okay. Now, within a single transaction, it's very important that the sequence of data updates is kept maintained properly. So every step in the process has to happen as a unit, and every process step either succeeds, thereby enabling the next step, or fails and aborting the process. For example, if you did an inventory update before you'd verified that the credit card was validated, right, that would be a problem. Or if you did other kind of supply chain updates before the payment was actually received. So you want to make sure you're doing these in order. So this goes back to what we were talking about earlier about consistency, about isolation for our ACID properties. You want to do things in the proper sequence so that the state of the database makes sense, right? It wouldn't make sense to say that we're down 1 unit of inventory because the credit card transaction failed. That would be a problem. Okay, now here we get into the interesting problem. So in principle, it's a bad idea to let multiple users access the same data simultaneously. In that case, you get what are called dirty reads. Okay, so this is a problem. We'll talk about this. Go to Paint. What happens when multiple users attempt to access the same data simultaneously? Okay, well, let's talk about that. This is potentially a big problem, right? Sure it is. Example 1, right? 2 users attempting a simultaneous withdrawal from the same bank account. Okay, that's potentially a problem. Number 2, 2 users attempting to reserve the same airline seats on the same flight at the same time. Okay, or any other sort of reservation type system. Any other reservation system, like concert tickets, back when we still had concerts, haha. Or what else? Two customers attempting to buy the same last product of a particular item. Okay, the same last particular item, whatever. It's the last one in stock. Okay, so all these, you got to make a decision somehow, right? In essence, if you let multiple users attempt to claim the same resource, there's trouble. Okay, but the seriousness of the trouble can vary widely. All right, so something like this, for example, if you have 2 users attempting a simultaneous withdrawal from the same bank account, that's potentially a huge problem, right? Because they could pull out the money twice and then it's all gone. They could try to clean out their account twice. Likewise, two customers attempting to buy the same last product of a particular item, well, that depends, right? So I could say, for example, a product that is one of a kind, right? Then that would be kind of serious because you can't fulfill one of those customer orders. Or a product that will have a new shipment, shipment arriving same day, right? So suppose we're talking about something that's a pretty big seller, like, I don't know, say, whatever the top best-selling book of the day is. Yeah, okay, maybe it says there's only one left in stock. If both people buy it, well, guess what? It's a bestseller. There's probably another crate of those books showing up inside the next 15 minutes anyway. It's not going to be a big deal. Okay, so depending on what's going on, sometimes the same data access simultaneously is a very big and serious problem, sometimes not so much. Okay, but we'll talk about what we mean by dirty reads. Dirty reads are when the two customers don't see the correct information, right? One of them maybe does, one of them doesn't. Commonly, this is done by interleaving of read and write operations. So we'll give a good example with ATMs. I'll do it in green for money. Okay, so here I am, ATM 1, ATM 2, okay? And this is me, and over here is ATM 2. And who's using it? My wife, okay? She's but shared account. So we both go to the ATMs and we try to withdraw some money. And let's say our daily withdrawal limit, well, let's just keep it even simpler. Let's say we have $500 in our joint account. Okay, so that's fine. We have $500. Now, what's going to happen? We show up at the same time. So number one, I attempt to withdraw $500. And number two, she attempts to withdraw $500. Okay, now what should happen at this point, I'll move these things down, is something like this. Yeah, it wasn't working. What should happen first, I see $500 balance. Likewise, she sees $500 balance. And both of those are true, right? At the time we go to the ATM, neither of us has pushed through an order. Yeah, neither of us has pushed through a transaction. So these are actually both correct. So I'm going to box those in green. Okay. We can both attempt to withdraw $500 at the same time. We can do that. But what's going to happen? Well, there's two possibilities. Number one, the way it should work, okay, the way it should work would be one or the other of us, number three, right, gets the $500. Meanwhile, her operation is blocked temporarily, okay, because simultaneous access is a problem, okay. Number five, I see balance of 0, and number six, she sees balance of 0. Okay, that's what should happen. What should happen is essentially this operation here should all be one logical unit. It should happen in isolation. The system should say, you're trying to access this account. Well, no, there's this stuff going on, and you can't access that information while it's in an intermediate state in the middle of a transaction, so you get blocked. Then once this is done, she sees the balance is $0. Okay, that's the way it should happen. However, what could happen is this. I attempt to withdraw $500, okay, but instead of getting the $500, what's happened is this. Database write, okay, on one replica says the balance is 0. But possibly she's reading from a different replica and also gets the $500. Okay? And then that replica reads $0. Okay, that is a possibility. The bank is out 500. I'm going to write the danger zone in red here. True balance, negative $500, right? We get an extra 500 due to bank carelessness. Okay, this is a problem. Now, yeah, it's not the end of the world if a bank has, a $500 loss, but the problem is if somebody can figure out a way to do this once, they can figure out a way to do it over and over, right? This is a problem. Or, for example, the user can get simultaneous access to 2 credit cards, use them simultaneously on every website on Earth, buy a whole bunch of stuff at the exact same time. So in practice, what happens, like I said, there's going to be some governing process that says, this data is temporarily locked while the transaction is processing. Come back in a few minutes and we can access the correct state. Okay, now if you say, what people might be thinking at this point, they're going to say, but wait, this all seems really obvious. And sure, for humans operating face-to-face, it is, okay? But when you have large-scale automated systems, not so much. It's not so obvious, okay? So again, what should happen, any access to data should first check if that data is being used by another update process and therefore unavailable, okay? But of course, not all systems are well designed. And we'll eventually talk, there's a big one, the Poloniex Bitcoin, I could say Bitcoin, I'll do it, yeah. Bitcoin exchange hack cost them about 20 million, okay? Essentially what happened, the attackers pushed through a whole bunch of simultaneous transactions and overdrew massively from the account. Okay, so the system was set up that, yeah, they assumed it would take a while for transactions to go through. Their system was designed to catch transactions happening at that speed, but these attackers launched a bunch of transactions at the level of microseconds, and they managed to get a whole bunch of money out of their account before the exchange actually figured out what happened. So again, in a well-designed system, this sort of thing shouldn't happen, but not all systems are well designed. Okay, now what can often happen in a system at the scale of Amazon, some operations are necessarily going to overlap. Okay, if you have a popular item, for example, and there's a lot of people buying it, there's thousands of people buying it every day, you may have a problem with overlapping operations on that data, right? So all the transactions that you want to do that are associated with it, if you try to do them in real time, basically the system's going to get backed up and people are going to have to wait. And what would happen then is somebody would try to buy something on Amazon, the credit card wheels would spin for a while, and then it would eventually say, sorry, your operation cannot be processed at this time. And the bigger the operation gets, the more likely something like that is going to happen, right? If people are buying lots of shopping carts full of stuff and every transaction involves accessing multiple parts of the database, yeah, that's a very serious problem. So the 3 practical resolution options, number 1, throttle the transaction rate, right? Basically slow down the pace at which people can perform transactions. Well, that's not generally going to be feasible, right? Amazon doesn't want to tell people, oh, I see you want to buy something. Well, we're really busy right now. Why don't you come back in a couple hours when things settle down, right? That's not what customers want to hear. Number two, splinter the operation. That's possible to a point, okay? But you can't always perfectly guarantee that it's going to work. So one of the things they do, for example, is they'll maintain multiple copies of data, right? So, right, in various ways, splintering, users don't lock up large parts of the system with one transaction, right? So, for example, you keep multiple replicas of the data like Facebook does. So if you're going to say things like number of items in stock, okay, you might do something like that. You might have multiple copies of that somewhere, and then they could be, what is the word, eventually consistent. Okay, so yeah, and there's the possibility that somebody might get a dirty read at that point because the replicas are not consistent. If they read from one or the other and they're showing different values, they can't both be right. Okay, they could both be wrong though. Okay, so that's a possibility. Yeah, that's fine for now, I guess. Or in some cases, you permit some simultaneous data access, right? Well, that's what we're doing here. Basically, when you're keeping multiple replicas of the data, okay? I would also add, let me add that here for splintering. Another possibility, keeping popular data in RAM, okay, for much faster response. But again, this is expensive, and many operations could involve both popular and less popular data. For example, a popular bestseller bought with a set of other less popular items. Okay, so you could do that. You could keep the most popular data in RAM, but that's not necessarily going to solve your problem because it's always going to be, in retail settings, it's always going to be mixed up with other data. So there are different solutions to the problem. Okay. But the one that we're interested in, right, permitting some simultaneous data access. So let's talk about that. What happens if multiple users simultaneously try to buy the same last item? Well, again, if it's the last one of its kind, then somebody's going to be pretty upset, right? If it's just the last one that Amazon has in stock this hour and there's a new shipment around the corner, then it's not a big deal. On the other hand, if two people attempt to use the same gift card or attempt to, use the same credit card simultaneously in a bunch of different locations, that could be a real problem if people get away with it. So the typical solution to that, something called locking. And locking just means if one user is using a particular thing, it gets locked so that nobody else can use it, right? And this can be applicable to data rows, data fields, whatever's stored in your data. You can say, somebody's doing something with this data, nobody else can access it, right? Works the same way with cards. So if you contact the credit card company while the transaction is going through to your account will be temporarily locked up. It'll say, okay, we're already processing one transaction. If another one comes through like a millisecond afterward, the credit card company is going to say, oh, sorry, no, that particular card is being used at this time. Come back in a few minutes. But locking doesn't solve everything all by itself. There's some follow-up problems with that. So number one, how long should a lock last? Okay, so an example, suppose there's a concert the next day and it's a very big popular concert and it's sold out. Okay, well, better yet, no. Let's say there is a concert, tickets have just gone on sale, right? Somebody buys a whole slew of tickets because they have preferred access, right? They have like 100 tickets they can buy, and they just let them sit in their cart. Okay, it's a popular concert, those tickets are going to sell. You got to let the user have a reasonable amount of time, like at least certainly a few minutes, to figure out what they're going to do with those tickets. But you probably don't want to let the lock last until after the concert's over and nobody can buy it. Okay. Another question, how many things can a single user lock, right? It would be kind of insane if somebody could go to Amazon and add every product on Amazon to their shopping cart and thereby deny anyone else the ability to buy it. Okay, that would be a problem. In practice, Amazon limits you to 100 items, last I checked. So that's the limit of what one user can lock up. So these are basic policy questions. There's not one inherent right answer. It's always a trade-off. So making a lock last longer is nice in terms of customer service, right? If something goes wrong with the process, or if the customer needs some time to figure out whether they really want to buy this thing or not, or how they're going to buy it, yeah, it's fair to let the lock last for a while. And I have, gone on to Amazon, had products in my cart, and seen them still there like days afterward, like maybe even a week afterward. But it all depends. It depends on how popular the product is, what the time of year is, right? If it's a popular toy and Christmas is around the corner, you don't want to have those locks last too long. So it's very situational. Okay, related problems, deadlock and livelock. So here we'll talk a little bit more about those. So in deadlock, you have two database operations that block each other. Okay, so I'm going to do an example for this. And talk. Imagine if there's two updates operations, right? So two update operations. Number one, operation A wants to update rows U, then V. Okay, and there's a second one, operation B wants to update rows E, then U, right? So same rows, but different sequence. So what can happen? Well, you can have the case where, number one, A updates and locks U. Meanwhile, B updates and locks V. Okay, then when A attempts to update V, it sees that V is locked. So it waits. Okay, likewise, number four, right? When B attempts to update U, it sees that U is also locked. So it waits, right? And the only way this breaks down, the deadlock ends when both processes time out, which could take a while. So this is essentially what deadlock is, right? You have two processes, and because of the way they're structured, they're going to force the other to wait, but the other one is also forcing it to wait, and so nothing happens. The system grinds to a halt. Thus, the emphasis on deadlock, because the system isn't doing anything, it's just waiting. Okay. And again, once you have deadlock, by the way, deadlock can spiral. If you think about this same thing, right? Once there's a deadlock happening, any other operation involving those records will also be blocked. So imagine if each operation, right, had a whole set of updates, and the deadlock happens. Okay, then it's going to be pretty bad. All right, pretty soon your whole database will get locked up. Okay, so that's the problem. That's how deadlock can happen, and it is a serious problem, especially at scale. Serious problem, especially at scale, where many users might reasonably attempt to access the same data, viewing the same product's inventory status. Okay, this is a serious problem. So, The other one, we talk about Livelock. Okay, Livelock is similar, but it happens when trying to resolve a deadlock actually keeps it going. Okay, so we're gonna back off a bit from all this. We're gonna do. Okay, so we have the same update operation. Okay, A does this, does this. Okay, but instead of just waiting, it does something. I'm trying to delete this. There we go. So what happens in Livelock? The system is still responding, just not doing anything to close out the transaction. So for example, what might happen, both processes might abort and retry in reverse order. Okay, that's clearly not going to solve anything, right? Because if A is updating V and B is updating U, they're still going to have their next step try to access the other one, or wait a fixed time like 3.000 seconds and try again. Well, what would happen then if this process happens, right? They both identify that the other record is locked. They both give up, come back in exactly 3 seconds. Well, the same thing is going to happen, because just as A is locking U, B is going to be locking V, and the same problem is going to happen, right? So Livelock is really very comparable, very comparable. Livelock is a lot like two people walking toward each other in a narrow hallway. Okay, because what happens? First, they both move to the side, right? But they're on the same side again, right? So they giggle and both move back, but they're still on the same side, okay? Eventually, one steps aside and they pass, okay? So Livelock is basically like that, right? I know we've all experienced this situation, but that's what we're doing here. Now, in this case, the Livelock does eventually get resolved, but that's what Livelock is. Both people in the process, they're doing something, but the doing something perpetuates the problem. Okay. So let's, I'm just going to do one more slide, and then we'll leave off the rest of this till another time. So your transactions for this sort of retail operation in particular, they follow this kind of standard request agreement sequence, right? So the basic model is the user tries to add something to the cart. The enterprise, say Amazon, either agrees to it or not, says, yeah, okay, you can add it, or no, we're suddenly out of stock. And then eventually you browse around some more. Eventually, maybe you check out, then the transaction happens. Or maybe it doesn't, because there's some fraud checking on the credit card, or there could be hardware failures, whatever. But basically, this kind of request agreement sequence. You try to do something, and the system either gives you a thumbs up or a thumbs down on it, right? And it's not all within Amazon. Could be other operations involved, like credit card verification, or you pick a particular shipping option, and then maybe you find out for whatever reason that shipping option is not currently available, and you get booted back to the prior screen, whatever. In any case, if you have a well-designed system, the final changes to the data don't happen until everybody involved has committed to the transaction. You have this kind of intermediate state where you're penciling in the changes, but until they've been finalized, they stay just that, right? You don't make the final changes to the system. Okay. So we'll come back on, on Tuesday, and then we'll talk about some transaction models, concurrency, and eventually we will get into the big ones of two-phase commit. Bum, bum, bum. All right, but that's all I got for you here today. So let's see how things are. Okay, so I'm going to stop the recording.